Hello and welcome to this clip having a look at a KP and controlling position of equilibrium question. So the first part wants us to predict with a reason whether the forward reaction is exothermic or endothermic. So to do that you need to look at what's happening to the temperature as it increases. So if the temperature goes up and what happens to KP, it goes down. So let's think about what this means. If Kp is decreasing, then that must mean the denominator is going up. So you're dividing the numerator by a bigger number to make the overall answer, Kp, smaller. So that must mean that when the temperatures increase, the reverse reaction must be endothermic, because what you're doing is increasing the pressure, partial pressure of the reactants. So these are increasing and the product is decreasing. So increasing the temperature makes the reaction go backwards. So therefore the reverse reaction is endothermic. So it would follow that the forward reaction is exothermic because the partial pressure of the reactants increases with temperature as Kp goes down. So the next part is stating and explaining in terms of Kp how you'd expect the equilibrium position to change if you increase the pressure but keep the temperature the same. So pressure is connected to the number of moles of gaseous molecules on each side of the equation. And you also need to remember that if it's the same temperature, that the value of Kp will stay the same, even though the ratio of reactants to products might change. So let's take our Kp expression and think about what happens when you increase pressure. Because all of the species are gases, that must mean that all concentrations will go up initially. So that's two partial pressure terms increasing in the numerator, and there are three partial pressure terms increasing in the denominator. So the denominator goes up by more than the numerator. So the value of the ratio would decrease because the denominator now represents a bigger number. So notice I'm not calling it Kp anymore because the temperature has stayed the same. We call it a ratio. So to make that ratio equal Kp again, in other words, to restore Kp, the numerator, the top part of the Kp expression, would have to get bigger. So the partial pressure of nitrogen dioxide would have to increase. To do that, the position of equilibrium would have to shift to the right. So in terms of the Kp expression, the numerator partial pressure terms increase, whilst the denominator partial pressure terms decrease. This restores Kp to its original value, and therefore you can call the ratio Kp again. So let's have a look at the mark scheme and see what they want. They want us to mention exothermic and Kp decreases, so we got that one. We had to say something about equilibrium shift, which we did. The effect of increased pressure on the Kp expression, and also something about the equilibrium shift in the Kp expression. So there's quite a lot of flexibility in the wording, but you can see that the way they're talking about it is in terms of the Kp expression, not the Chatelier's principle. The only mention is the shift to the right. Okay, thanks for listening. Until next time, see you soon.